Oh. Thanks for joining us, friends. I'm getting ready to read to everybody here. There are a lot of folks that wish to pursue natural farming, and there's a lot of information that goes into that. It's really a lot that you need to understand going into it, versus going and finding supplements at the store and doing a hydroponic setup without concern for live soil and no-till, or the soil food web, the microorganisms in the soil. We already read the preface in chapter 1 the other day, and it was basically covering Jeff Lowenfeld's journey going from growing and using fertilizers from the store to using the help of the microorganisms in the soil. We talked a little bit about the soil food web yesterday, the microorganisms therein, the different relationships they have with each other. Talked a little bit about the different sources of nitrogen, and how certain plants would like this nitrogen from a particular source. And when you're growing with supplements, salt-based fertilizers, something like that, it's one type of nitrogen source. And some plants aren't for it all the time, and it was something that, just to sum it up, when you're using, like I'm using salt-based fertilizers and general hydroponics, Flora Nova line, liquid-based supplements. When you use these, the plant is totally all for it and will take the boost and grow, but it does not actually build up these defenses when they have this relationship with the microorganisms in the soil you can cultivate. The bacteria and the fungi themselves will bond with the plants and do things to help create natural barriers and defenses from invasive microorganisms and critters and stuff. Symbiosis! Yes, exactly. It's a beautiful thing, ain't it? Super cool. Yeah, so we learned a little bit about that, how through chapter 1 it had noted that the plants can build natural defenses using the relationships it has with the microorganisms in the soil, versus the defenseless boost and route of going buff with salt-based fertilizers and stuff. Crazy. Yeah. So today we're reading chapter 2 and 3. Don't mind me, I'm just kind of getting settled in here. And hyping myself up, preparing, Yeah. It's been a little while since I've actually gone and read full text and read aloud to others, so if I stutter on something or speak too fast, let me know. Alright. One more time. Teaming with Microbes. The Organic Gardener's Guide to the Soil Food Web. Revised edition. Jeff Lowenfels and Wayne Lewis. Chapter 2. Classic Soil Science. This would be a good time to go outside and get a few handfuls of soil from different places in your yard. Take a good, close look at the soil. Smell it. Grind some between your fingers. Compare the samples for differences and similarities. When you repeat these observations after you read this chapter, you will have a different perspective of what is in your hands. The typical gardener knows very little about soil and why it matters. To us, however, soil is the house in which all of the organisms of the soil food web live. It is the stage for the actors that interest us. You simply have to know something about the physical nature of soil if you are to understand the biology that inhabits it, and how to use this biology to become a better gardener. After all, an acre of good garden soil teems with life, containing several pounds, about 1 kilogram, of small mammals, 133 pounds of protozoa, 900 pounds each of earthworms, arthropods, and algae, 2,000 pounds of bacteria, and 2,400 pounds of fungi. Most of us, if we want things to grow better, simply replace soil that is poor in quality with good soil. Experienced gardeners know good soil when they see it. Coffee-colored, rich in organic matter, able to hold water, yet still drain when there is too much around, and it smells good. Poor soil is pale, compacted, drains either too well and won't retain any water, or holds too much water, sometimes even becoming anaerobic. We were just talking about that, anaerobic environments, the other day. Yeah. If you're going to use the soil food web, however, you really need to know more. Where does soil come from? What are its components? How can we agree to describe it, and how can we measure its characteristics? This knowledge will help you adjust your soils. For what determines really good soil, in the end, is what you wish to grow in. Good soil must be able to maintain a soil food web compatible with the plant it supports. Sorry, let me read that again. Good soil must be able to maintain a soil food web compatible with the plants it supports. Trust us. In the end, you will be glad you know a little something more about soil, something beyond its color and smell. What is soil really? Technically, soil is all the loose, unconsolidated mineral and organic matter in the upper layer of the Earth's crust. The standard comparison uses an apple to represent the Earth. Carve off approximately 75% of the skin, which represents all the water, and another 15%, which represents desert or mountains, land too hot, too cold, too wet, or too steep to be usable for growing plants. The 10% that remains represents all the Earth's soil. Soils with the necessary physical, chemical, and biological properties to support plant life. When we take into account the footprints of cities, roads, and other man-made infrastructure, these, incidentally, usually are sited on some of the very best soils. The surface area of usable soil is further reduced. For the moment, the thing that concerns us is the tiny strip of apple skin that represents the soil in our gardens and yards. How did it get there? What is it? Why does it support plant growth? Yeah. Hey Jake, how's it going, man? I hope you're doing good today. Welcome back. Oh. We're reading Teaming with Soil, chapters 2 and 3. Weathering. Your yard's soil is in large part a product of weathering. Weathering is the sum impact of all the natural forces that decay rocks. These forces can be physical, chemical, or biological. To begin, the mere action of wind, rain, snow, sun, and cold, along with glacial grinding, bumps along riverbeds, scrapes against other rocks, and rolls in ocean waves and stream currents. Physically, break rocks down into tiny mineral particles and starts the process of soil formation. Water freezes in rock cracks and crevices and expands, increasing its volume by 9% and exerting a force of about 2,000 pounds per square inch as it turns to ice. Hot weather causes the surfaces of rocks to expand, while the inner rock, just a millimeter away, remains cool and stable. As the outer layer pulls away, cracks form, and the surface peels off into smaller particles. Chemical weathering dissolves rock by breaking the molecular bonds that hold it together through exposure to water, oxygen, and carbon dioxide. Some materials in rock go into solution, causing the rock to lose structural stability and making it more susceptible to physical weathering. Think of a sugar cube dropped into a cup of tea and then stirred. Fungi and bacteria also contribute to chemical weathering by producing chemicals as they decay their food. Fungi produce acids and bacteria alkaline substances. Besides carbon dioxide, microbes produce ammonia and nitric acids, which act as solvents. Rock material is broken down into simpler elements. Although there are almost 90 different chemical elements in soil, only 8 constitute the majority: oxygen, silicon, aluminum, iron, magnesium, calcium, sodium, and potassium. All have an electric charge on a molecular level, and in different combinations, these form electrically charged molecules that combine to form different minerals. Ooh, that's a nice picture. It's got a massive picture of lichen that's yellow. It says, the acids produced by the yellow lichen on this rock are slowly contributing to its conversion into soil. So the lichen is legit breaking down the rock. I did not know that's what it do. That's awesome. Yeah. There's a lot of us that are down with the gardening and the cannabis and the processing. Right now we're trying to learn about the soil and stuff. So for us, we're having a discussion about this. It's in the title, Teaming with Microbes, Chapter 2 and 3. So, yeah, if you're down to hear me out on that, I'm going to continue on this for now. There's some folks in chat that definitely have all that information, so, maybe someone do know. Yeah. Oh, absolutely, yeah. What was it? There's Paul Stamets, 6 Ways Fungus Can Save the World, TED Talk. He talks about that. We have a similar makeup, like our cells are very similar to the cells that make up fungi. Yeah. Okay, sorry. Getting back to the book. Biological activity, too, causes weathering. Mosses and lichen, or more precisely, the fungi in them, attach themselves to rocks and produce acids and chelating agents that dissolve little bits of rocks to use as nutrients, resulting in small fissures that fill up with water. Freeze and thaw cycles further break apart the parent material, and the roots of larger plants penetrate crevices and widen them, forcing rocks apart. Holy shit! This is awesome. I've always just looked at how the wind and the water cut into the rock, but I never understood that it was actually that as well. The lichen and the fungi within the lichen and the mosses that are consuming the rock and breaking it down as well. Holy crap. Wait. Sorry, one more time. Yeah. Collating agents? Collating agents, then? Yeah. Collating agents. Alright, sorry, one more time. Biological activity, too, causes weathering. Mosses and lichen, or more precisely, the fungi in them, attach themselves to rocks and produce acids and collating agents that dissolve little bits of rock to use as nutrients, resulting in small fissures that fill up with water. Collate? Yep, collating. Chelate. Organic matter. Weathering breaks rock down into mineral components of one sort or another. Soil, however, needs to be able to support plant life, and that requires more than just minerals. On average, good garden soil is 45% mineral in nature and 5% organic matter, built up as organisms above and in it go about their daily business. As plants and animals on the surface die and are decayed by bacteria and fungi, they are ultimately converted into humus, a carbon-rich, coffee-colored organic material. Think of the end product of composting. This valuable material is humus. I always talk about it. Humus is like the black gold of the soil. Humus consists of very long, hard-to-break chains of carbon molecules with a large surface area. These surfaces carry electrical charges, which attract and hold mineral particles. What's more, the molecular structure of the long chains resembles a sponge. Lots of nooks and crannies that serve as veritable condominiums for soil microbes. Once you've added humus and other organic matter, such as dead plant matter and insect bodies, to weathered minerals, you have a soil almost capable of supporting trees, shrubs, lawns, and gardens, but not quite. Air and water. Minerals and humus make up the solid phase of soil, but plants require oxygen and water, the gaseous and liquid phases as well. The voids between individual mineral and organic particles are filled by air and water, and sometimes both. And there's a picture of humus. Yeah, sorry. That's what's right there. Humus has a rich coffee color and is full of organic material. This handful is about 55% organic matter. Right there. It just looks like really black, thick chunks of the dirt when people look at it. Lightweight-ish, spongy, yeah. Water moves between soil pore spaces in one of two ways: by the pull of gravity, or by the pull of individual water molecules on each other, or capillary action. Gravitational water moves freely through soils. Picture water being poured into a jar of gravel. Gravity pulls the water to the bottom as the jar fills up. Large pores promote the flow of gravitational water. As the water fills the pores, it displaces and pushes out the air in front of it. When the water flows through, it allows a new supply of air to move in. When gravitational water hits roots, which acts like sponges, it is absorbed. Smaller soil pore spaces contain a film of capillary water that is not influenced by gravity, and is actually left behind after gravitational water passes through. The liquid is bonded together by the attraction of its molecules for each other, a force known as cohesion. But let's not complicate things. and to surrounding soil surfaces, a force known as adhesion. This creates a surface tension, causing the water to form a thick film on the particle surfaces. Capillary water can flow uphill. It is available to plant roots after gravitational water has passed by, and as such is a major source of water for plants. Hygroscopic water is a thinner film of water, only a few molecules thick, which, like capillary water, is attached to extremely small soil particles by virtue of electrical properties. This film is so thin that the bonds between water molecules and soil particles are concentrated and extremely hard to break. Roots cannot absorb it. Therefore, but this film... what? Roots cannot absorb it, therefore, but this film of water is critical to the ability of many microbes to live and travel. Even when conditions are dry, the soil particulate surface holds some hygroscopic water. It is impossible to remove it from soil without applying lots of heat and actually boiling it off. Just about half the pore spaces in good soil are filled with water. The other half are filled with air. Water movement pushes stale air out and sucks in air from the surface. So adding water means an exchange of air occurs, which is important. If a healthy soil food web is in place, the metabolic activity of soil organisms uses the oxygen and creates carbon dioxide. One more time. If a healthy soil food web is in place, the metabolic activity of soil organisms uses the oxygen and creates carbon dioxide. There you go. The presence of carbon dioxide is a good sign that the soil contains life. However, the carbon dioxide must be exchanged with fresh air to keep life going. In some soils, the pore spaces are cut off in lots of places, and air is not exchanged when water flows. In fact, water may not flow at all. These soils have very poor porosity. That is, they lack adequate space between the soil particles. All the oxygen in the soil can be used up by aerobic metabolic activities, resulting in oxygenless anaerobic conditions. Organisms that can live in such conditions often produce alcohols and other substances that kill plant root cells. So that's what happens when you create an anaerobic environment. I've been fucking trying to understand more about that, because people, Tony mentioned it to me? And I was trying to understand more as I've been understanding the balance of bacteria and fungi in the soil. Which is about 0.6 to 1 to 1 ratio of bacteria to fungi in the soil for cannabis, and a lot of crop. About a 1 ratio for your gardens and such. Now you know why. Creating an anaerobic environment creates microorganisms that produce alcohols that kill the plant cells, on top of the lack of oxygen in the soil that's healthy for everything else that's trying to live there. Yeah. Very cool. Hey, I grew some. How's it going? Hey, hope you're good. Yep. Is this book factual? Shut the front door. Yeah, dude. Yeah. Oh, God. We're sitting here talking about the actual science of this stuff, and you're saying, is this book factual? Like, come on. Yeah. Hey, man, scientists wrote this book. Yeah. And I went to seminars myself to learn about this from folks that worked with Jeff Lowenfels, and took samples myself, and my field training is something that I look to this, and makes sense to me, really isn't magic. I'm not sitting here trying to get all Harry Potter with it. Definitely. But that was very silly. A lot of the conversation I guess we've been having lately is silly. You're more than welcome to sit, listen to me read along and stuff, but I have not forgotten all of the conversations that we had. So think about that before you say something else, Lick Frogs. Yeah. Soil profiles and horizons. Soils are exposed nonstop to the forces of weathering. Rain, for example, will cause some soil minerals and organic matter to leach out as the water moves down through the soil. This material may hit an impervious barrier and become concentrated in a certain zone and layer. The size of particles may cause a particular material to be concentrated or be filtered. Eventually, over time, distinct layers and zones of different material are formed. These can be seen, like the rock strata in the Grand Canyon's walls. As you dig down through the soil, a soil profile is a map of these layers or horizons. Soil scientists have attached a letter or combination of letters and even numbers to each horizon that appear in any typical soil profile. For the gardener, thankfully, the top horizons, the O and A, are really the only ones that count. The OI horizon contains organic material that can still be specifically identified, with a bit of training that's beyond the scope of this book. This is fibric soil. The OE horizon has experienced more decay, and while the materials are identifiable as plant matter, you cannot tell which specific plants are involved, even with training. This is humic soil. Finally, the OA horizon is where the organic material has decomposed so much that you cannot tell its origin. It could be from plants or from animal matter. This is sapric soil. All this is somewhat useful information if you want to know if your soils will create more decay byproducts, like nitrogen, because the process that converts the soil to humus is incomplete. Or if your soil has been decayed to the point where it basically just houses microbes that cause decay. Yeah. The A horizon lies under the O horizon, where humus particles accumulate as water runs through the O horizon above and pulls organic particles downward. Water flowing through this horizon carries lots of dissolved and suspended materials. This A horizon has the highest organic matter content. Any of the soil horizons This A horizon has the highest organic matter content of any of the soil horizons and the highest biological activity. This is where the roots grow. Several other soil horizons follow, and eventually bedrock. You would need a backhoe to trench through all the horizons under your yard, something that is clearly not worth the effort. Often one or more horizons are missing, worn, or transported away by weathering forces, and just as often it is too hard to see any distinction between layers. The important thing is to make sure your gardens and yard have good soil, the proper mixture of minerals, organic matter, and air in top layers, in the area where plants grow. If not, you will have to add what you do have or replace it entirely. Oh my. Soil color. Color can be an easy indicator of what is in your soil, as soil color is sometimes dependent on the soil's specific mineral and organic components. Weathering, oxidation, reduction actions of iron and manganese minerals, and the biochemistry of the decomposition of organic matter are the primary factors influencing soil color. Organic components in soil are very strong coloring agents and produce dark soils. These can accumulate or can dissolve and coat other particles of soil with black color. When iron is a component of soil, it rusts, and soil particles are coated with red and yellowish tints. When manganese oxide is a major component of soil, its particles turn on a purple-black hue. The presence of these colors usually indicates good drainage and aeration. Gray soils can indicate a lack of organic material. They also often indicate anaerobic conditions, because the microbes that survive in such conditions often use the iron in the soil, rendering it colorless in the process. Similarly, magnesium is reduced to colorless compounds by other types of anaerobic soil microbes. Soil scientists use color charts to identify, compare, and describe soil conditions. For the gardener, however, color plays less of a role. For us, good soil is the color of dark coffee. Again, mostly because of its organic components. Soil texture. Soil scientists describe the size of soil particles in terms of texture. There are three categories of soil texture: sand, silt, and clay. All soil All soil has a specific texture that enables one to judge its propensity to support a healthy soil food web, and thus healthy plants. Soil texture has nothing to do with composition. If you think the term sand applies only to quartz particles, for example, you would be wrong. True, most sand particles are mineral quartz, but all sorts of rock can be weathered into sand. Silicates, feldspars, potassium aluminum silicate, sodium aluminum silicate, and calcium aluminum silicate, iron and gypsum calcium sulfate. If the sand comes from ground up coral reefs, it is limestone. Most silt particles, too, are mineral quartz, only they are much smaller in size than those found in sandy soils. And silts can have the same non-quartz constituents as sand. Clay, on the other hand, are made up of an entirely different group of minerals. Hydrous aluminum silicates and other elements, such as magnesium or iron, occasionally substituting for some of the aluminum. So the key point for the gardener is that texture has to do with the same size particle. Let me reread that. So the key point for the gardener is that texture has to do with size of particles only, not the composition of these particles. What size particles then constitute sand, silt, and clay? Start with sand. You've undoubtedly been to a beach and know that sand particles can be seen with the naked eye. They range in a size from 0.0625 to 2 millimeters in diameter. Anything much bigger has far too much space between individual particles to be of any use to gardeners, except as gravel for a path. Sand particles are just small enough to hold some water when aggregated, but most of it is gravitational water and readily drains out, leaving lots of air and only a little capillary water. Moreover, the particles of sand are big enough to be influenced by gravity, and they quickly settle to the bottom when mixed with water. Mixed in water. As to texture, soils with large proportions of sand in them are gritty when ground between the fingers. Next in texture size is silt. Sand particles can be seen with the naked eye, but you will need a microscope to see individual silt particles. Like sand, these consist of weathered rock, only much, much smaller in size, between 0.004 and 0.0625 millimeter in diameter. The pore spaces between silt particles are much smaller and hold a lot more capillary water than sand does. Like sand, particles of silt are also influenced by gravity and will settle out when put in water. The texture of silt, when rubbed between fingers, is that of flour. Clays are formed during intense hydrothermal activity or by chemical action, that of carbonic acid weathering silicate-bearing rocks. Clay particles are readily distinguished from silt, but this time an electron microscope is needed These particles are that small, the smallest that make up soil, 0.004 millimeter across or less. Clay particles are plastic and somewhat slippery when rubbed between fingers. This is because clay particles absorb and hold lots of water, which is why they are known as hydrous silicate compounds. Besides silicon, they contain water and often aluminum, magnesium, and iron as well. For comparison, let's put things into a more familiar perspective. If a clay particle were the size of a marigold seed, a silt particle would be a large radish, and a sand grain would be a large garden wheelbarrow. Another way to look at soil texture is to visualize a gram, about a teaspoon's worth of sand, spread out one particle deep. This would cover an area about the size of a silver dollar. If you were to spread out an equal amount of clay, one particle thick, you would need a basketball court, and some of the stands surrounding it at that. What difference does texture make? The size of the particles has everything to do with their surface area, and the surface area of the pore spaces between individual particles. Clay has tremendous surface area compared to sand. Silt is in between. Clay has smaller pore surfaces between particles, but many more pore spaces in total. So the surface area of the pore spaces in clay is greater than silt, which is greater than sand. Incidentally, organic matter, usually in the form of humus, is comprised of very minute particles that, like clay, have lots of surface area to which plant nutrients attach, thus preventing them from leaching out. Humus also holds capillary water. All soils have different textures, but any can be put into a specific category, depending on how much sand, silt, and clay-sized grains they contain. The ideal garden soil is loam, a mixture with relatively equal parts of sand, silt, and clay. Loam has the surface area of silt and clay to hold nutrients and water, and the pore space of sand to aid drainage and help pull in air. Yeah. Oh! Hey Crafty, I hope you're well. Yes, I'm reading Teeming with Microbes. At any time, you could look at the title of the stream below the broadcast. I don't know if this works. Yeah. There's also !stream that you can type and it gives you some information. You're always welcome to look at it. I am in chapter 2 of Teeming with Microbes, Classic Soil Science. Sample your soils. Good garden soil contains 30 to 50% sand, 30 to 50% silt, and 20 to 30% clay, with 5 to 10% organic matter. I think some of those numbers are off. You can find out how close to your soils come to this ideal loam. All it takes is a quart jar, 2 cups of water, and a tablespoon of water softener, such as Calgon liquid. You'll also need soil from the top 12 inches, 30 centimeters, of the areas you want tested, be it your vegetable garden, flower bed, or lawn. Mix each soil sample with 2 cups of water and a tablespoon of water softener. Put in the jar, close the jar, and shake it vigorously so that all the particles become suspended in the water. Then put the jar down and let things settle. After a couple of minutes, any sand particles in your soil will have settled out. It takes a few hours for the smallest silt particles to settle on top of this sand. Much of the smallest clay-sized particles will actually stay in suspension for up to a day. Organics in the soil will float to the top and remain there for an even longer period. Wait 24 hours and then measure the thickness of each of the layers with a ruler to describe the percentage of each. Divide the depths of thickness of each layer by the total depth of all 3 layers and then multiply the answer by 100. Once you know what percentages of each material are in your soil, you can begin to physically change it if needed be. How to do this is discussed in the second half of the book. That's awesome. So that was just a brief explanation on taking a soil sample and seeing how much of the soil and silts and clay is in your soil and the organic matter. 2 cups water, and a tablespoon of water softener, and then your sample of soil. Um, hmm. Yeah, you don't really need much. You can totally just take a freaking, like, less than maybe like a quarter cup as a soil sample for each of these into the 2 cups water, 1 tablespoon water softener. Shake it up and let it settle and measure that. Um, yeah. I was taking soil samples at the organic lavender farm I worked at to understand more about the microorganisms in there. It's been pretty nice so far, learning what we're learning, understanding what's in the book here on top of what I've already like seen. It's really awesome because it's like fucking putting pieces of the puzzle together. Um, yeah. Oh yeah. So yeah, just reading chapters out of Teaming with Microbes. I have Teaming with Nutrients and Teaming with Fungi, and I'll do my best to read a few chapters at a time with everybody. So thank you for hearing me out. Doing my best to read aloud, go through it without sounding like a jargle and stuff. Yeah. Oh no, this is gardening. It's beyond cannabis, bro. This is soil. This is the earth, the microorganisms within. Cannabis is just one of thousands upon thousands of plants that interact with the soil. You know. Yeah. Yeah. Sorry. Mm-hmm. So far, we were discussing components of the soil, what the soil is, what it makes up, and things that you can find within your garden that was considered good soil. We delved a little bit into what is anaerobic environment, where you're basically promoting this nasty or environment where there's anaerobic bacteria, microorganisms that produce these alcohols that are killing plant cells. Um, the thing that's like part of the plant, very important. You don't have the right environment for the rest of your microorganisms, the whole thing is just gonna go south from there. You know, plant defenses are down. The plant's literally dying in that shit. Yeah. So we learned about that. We talked a little bit right now about the minerals in the soil. The what was it? Sand, silt, clay, organic matter. Um, how that's all basically all up in your business. There was a discussion about these minerals that you can have in your soil that affect the color and components, like iron. Excess iron in your soil can promote rusting, and you will get this red color in your soil versus something that's like you got more humus and it's coffee colored. It's really good soil. It's got a good mixture of the organic matter as well. Oh yeah. There's a couple other materials that'll make that combo of stuff, right? Um, Heavy clay. Yeah, yeah. There's like that too, right? Black sands and rivers are iron rich. Yeah, that's I think what in that regard that's because of what was it? That's iron combined with salt, and then like what we were talking about the other soil and seeing it red and stuff. That's probably more clay based with iron as well, and so it has that red and orange appearance uh, from that itself. Uh, Science. Yep, and that's like yeah, mixed with water too, and like the environment where you would see like the clay compacted in the iron, there's less of the content of water. Something more notable in like desert areas or where it's dry and stuff. Uh, oh yeah, yeah, that guy, and his twin. Yeah, back to the reading. Teeming with microbes. Classic soil science. Chapter 2. Soil structure. Individual particulate size, or texture, is obviously an important characteristic of soils, but so is the actual shape these particles take when grouped together. This shape, or soil structure, depends on both the soil's physical and chemical properties. Factors that influence soil structure are particle orientation. Factors that influence soil structure are particle orientation, amount of clay and humus, shrinking and swelling due to weather, wetting and drying as well as freezing and thawing, root forces, biological influences, worms and small animals, and human activity. Soil structure types, or PEDs, fall into several distinct categories. When you look at your garden soils, you don't see individual particles, but rather aggregates of these particles. The biology in the soil produces the glues that bind individual soil particles into aggregates. As they go about their day-to-day business, bacteria, fungi, and worms produce polysaccharides, sticky carbohydrates that act like glues, binding individual mineral and humic particles together into aggregates. Yeah. Let's start with bacteria. The slime they produce allows them to stick to particles as well as to each other. Colonies are formed, and these too stick together, as do the particles to which the bacteria are attached. Fungi also help create soil aggregates. A group of common soil fungi in the order glomales produce a sticky protein called glomalin. A group of common soil fungi in the order glomales produce a sticky protein called glomalin. As the fungal strands or hyphae grow through soil pores, glomalin coats soil particles like superglue, sticking these particles together into aggregates or clumps. These aggregates change the soil pore space, making it easier for the soil to hold capillary water and soluble nutrients, and recycle them slowly to plants. Worms process soil particles in search of food. Individual particles of minerals and organics are ingested and completely excreted as aggregates. These are so large, they are readily identifiable as worm castings. Consider too the impact of soil organisms as they make their way through the soil. Each group of animals has various body widths. As they move, they create spaces in and between soil particles and aggregates. By way of comparison, imagine that a bacterium 1 micrometer in diameter, 1 micrometer equal to 1/25,000th of an inch, is the width of a piece of spaghetti. Fungal bodies are generally wider, 3 to 5 micrometers. Nematodes, 5 to 100 micrometers on average, would be the size of a pencil, perhaps even one of those thick ones. And protozoa, 10 to 100 micrometers, would be the diameter of an American-style hot dog. Continuing to use our scale, soil mites and springtails at 100 micrometers to 5 millimeters would have the diameter of a good-sized tree. Beetles, earthworms, and spiders, 2 to 100 millimeters, would have the diameter of really large trees. Imagine how each opens up soil particles as they go about their daily activities. Yeah. Worms are the forest champs, the digestive system of the forest. Hell yeah. Finally, electrical charges on the surfaces of organic matter and clay particles attract each other in addition to chemicals. Calcium, iron, aluminum, in water solution, acting as bonding agents that hold together soil particles. Why are we going over this soil structure stuff? Because soil structure is a key characteristic of good growing conditions. If there is adequate soil structure, there is ample drainage between aggregates, but also plenty of plant-available capillary water. The air circulation necessary for biological activity is sufficient, and perhaps most important. If there is adequate soil structure, there is space for soil biology to live. Good soil structure withstands torrential rains. The drying of desert-like droughts, herds of animal traffic, and deep freezes. Oh gosh, I read that as 2 sentences, sorry. Let me go off on this again. The air circulation necessary for biological activity is sufficient, and perhaps most important. If there is adequate soil structure, there is space for soil biology to live. Good soil structure withstands torrential rains, the drying of desert-like droughts, herds of animals, and deep freezes. Water and nutrient retention is high. Life in and on it thrives. Poor soil structure results in a lack of water retention, and soil collapses under all the above-mentioned environmental and man-made pressures. Little life is in it, and the serious reduction in fertility drives people to resort to chemical fertilizers in increasing amounts. Alright, so we got a really nifty chart here that talks about different soils. Hold on here. Let me see if there was something on the other page. Negative. Okay. Soil structure PEDs. So you've got at the top there, granular. Resembles cookie crumbs and is usually less than 0.5 centimeters in diameter. Commonly found in surface horizons where roots have been growing. Then you've got the blocky PED. Irregular blocks that are usually 1.5 to 5 centimeters in diameter. You've got prismatic PEDs. This type of soil structure has vertical columns of soil that might be a number of centimeters long, usually found in lower horizons. Columnar. Say that 5 times fast. Columnar. Vertical columns of soil that have a salt cap at the top, found in soils of arid climates. Where I live, I see a lot of platy soil structure. Thin, flat plates of soil that lie horizontally, usually found in compacted soil. Then there are single-grained. Soil is broken into individual particles that do not stick together. Always accompanies a loose consistency, commonly found in sandy soils, like beaches and other parts of the desert. Yeah. Massive. Soil has no visible structure, is hard to break apart, and appears in very large clods. Yeah. Oh, the OnlyFans is there. Yo bitch ass just won't subscribe. They just joke about it. Yep. Alright. Back to the book. Alright. Microscopic view of fungus growing on a corn root. The round bodies are fungal spores. The threads are fungal hyphae. And the green color is from dye tagged glomaline, the glue that holds soil particles together. Yeah. That's what that was there. It's on the green screen, so you just see the background slightly. It's pretty cool, actually. Yeah. Yeah. All right. Cation and Cation exchange capacity. All tiny particles, not just humus, carry electrical charges. These particles are called ions. Ions with a positive charge are called cations, and negatively charged ones, anions. Anions. Sorry. Let me read that again. These particles are called ions. Ions with a positive charge are called, so would that be cations? Or is that cations? Cation. Yeah. Cation. And negatively charged ones, anion. Positively charged particles are electrically attached to negatively charged particles. This is exactly what happens when opposite ends of magnets attract each other. When a positively charged cation attaches itself to a negatively charged anion, the cation is absorbed by the anion. Even microorganisms in the soil are small enough to carry and be influenced by electrical charges. I've talked about that before. Sand particles are too large to carry electrical charges, but both clay and humus particles are small enough to have lots of negatively charged anions that attract positively charged cations. The cations that are absorbed by clay and humus include calcium, potassium, sodium, magnesium, iron, ammonium, and hydrogen. These are all major plant nutrients, and they are held in the soil by two components of good soil. The attraction of these cations to the clay and humus particles is so strong that when a solution containing them comes into contact, the attraction is satiated and only about 1% of the cation nutrients remains in solution. Wow. There are anions in soil as well. These include chloride, nitrate, sulfate, and phosphate, all plant nutrients. Unfortunately, soil anions are repelled by the negative charge on clay and humus particles, and therefore stay in solution instead of being absorbed. These plant nutrients are often missing from garden soils, as they are easily leached away in the soil solution when it rains or soil is watered. Nothing is holding them onto the soil surface. Why does this matter? The surfaces of root hairs have their own electrical charges. When a root hair enters the soil, it can exchange its own cations for those attracted to clay or humus particles, and then absorb the cation nutrient involved. Roots use hydrogen cations as their exchange currency, giving up one hydrogen cation for every cation nutrient absorbed. This keeps the balance of charges equal. This is how plants eat. Oh yes. What was it? It's super cool. So I always talk about this myself about plant cells and how plants intake water. This is covered in Teeming with Nutrients. The plant is made up with plant cells. Water is absorbed through the root base, directly through plant cells, and in between plant cells, it goes through into different parts of the plant. These plant cells, like I was saying, there are the positively charged ions, the cations, that are entering and exiting the plant, taking what they need from the supplements that are going within. It's pretty crazy to see it at this level. Sorry. Don't mind me. The place where the exchange of a cation occurs is known as a cation exchanging site, and the number of these exchange sites measure the capacity of the soil to hold nutrients, or the cation exchange capacity. A soil's CEC is simply the sum of positively charged nutrient replacements that it can absorb per unit weight of volume. CEC is measured in milligram equivalents per 100 grams. Oh god. One more time. Milligram equivalents per 100 grams. What the gardener needs to know is that the higher the CEC number, the more nutrients the soil can hold, and therefore, the better it is for growing plants. The higher the CEC, the more fertile the soil, the more fertile the soil. You can order a CEC test to be run by a professional soil lab. The CEC of soil depends, in part, on its texture. Sand and silt have low CECs because these particles are too big to be influenced by an electrical charge and hold nutrients. Clay and organic particles impart a high CEC to soils because they do carry lots of electrical charges. The more humus, and to a point, clay present. Let me read that again. Clay and organic particles impart a high CEC to soils because they do carry lots of electrical charges. The more humus, and to a point, clay present in soils, the more nutrients can be stored in the soil, which is why gardeners seek more organics in their soils. Yeah. Slurry test is something that's easy to do. Yeah. I was trained to do the slurry test. Yeah. There are limits to a good thing. Don't forget that the clay particles are extremely small. Too much clay and too little humus result in a high CEC, but little air in the soil. But the pore space is too small and cut off by the clay's platy structure. Such soil has good CEC but poor drainage. Thus, it is not enough to know the CEC alone. You have to know the soil texture and mixture. Yeah. You were one of the ones that had mentioned that to us of doing the slurry test. That was really important when we were doing the slurry test for the soil to fucking see what was going on with the ppm, because there was something up with the water and stuff when we were draining the drain water to our plants when we were using that purple bag of sunshine mix number 4. Slurry test was the way we could fucking do the thing and see what was going on there with the ppm pH. For CEC, same shebang. You can see what's going on in there. Soil pH. Most of us have a basic understanding of pH as a way to measure liquids to see if they are acid or not. On a scale of 1 to 4, a pH of 1 is very acidic, and a pH of 14 is very alkaline, or basic, the opposite of acidic. The pH tells the concentration of hydrogen ions, a cation, in the solution being measured. If you have a lot of hydrogen ions compared to the rest of what is in solution, the pH is low and the solution is acidic. Similarly, if you have relatively few hydrogen ions in solution, then you have a solution with a high pH, one that is alkaline. As a gardener, you, fortunately, don't need to know much more about pH. You do need to understand, however, that every time a plant root tip exchanges a hydrogen cation for a nutrient cation, the concentration of hydrogen ions in the solution increases. As the concentration of hydrogen ions, what did I just see? As the concentration of hydrogen ions goes up, the pH goes down. The soil is increasingly acidic. Things usually balance out, however, because root surfaces also take up negatively charged ions, using hydroxy anions as the medium of exchange. Adding OH negative to the solutions raises the pH. That is, soil is increasingly alkaline because it lowers the concentration of H+. Fungi and bacteria are small enough to have cations and anions on their surfaces, electrically holding or releasing the mineral nutrients they take and form decomposition in the soil. Oh gosh, let me read that again. Fungi and bacteria are small enough to have cations and anions on their surfaces, Electric, electrically holding on, electrically holding or releasing the mineral nutrients they take in from decomposition in the soil. This too has an impact on the pH of the soil. Why is pH a consideration when we talk about the soil food web? The pH created by the pH created by nutrient ion exchanges influences what type of microorganisms live in the soil. This can either encourage or discourage nitrification and other biological activities that affect how plants grow. As important, each plant has an optimum soil pH. As you will learn, this has more to do with the need of certain fungi and bacteria important to those plants to thrive in a certain pH than it does with the chemistry of pH. Knowing your soil's pH is useful in determining what you want to put in your soil, if anything, to support specific types of soil food webs. And knowing the pH in the rhizosphere helps determine if any adjustments should be made to help plant growth. The rest of part 1 covers the biology that lives in the soil. You have to appreciate the soil first, however. Yeah. So that was chapter 1. Oh, sorry, chapter 2. Yeah. Oh my. So there we go. We were learning about the composition of the soils available, different types of soil, and how plants could get these supplements in the soil through the different combinations. Oh gosh. Sorry, I think I was more so trying to say we learn more about the health of the soil through the different types. Huh? That was groovy. Mm-hmm. Oh. Mm-hmm. Yeah. Which one? Oh yeah. Okay. Yeah. That was crazy. The color on it. That was the one from outside. Oh yeah, that like dried out and it like looks. Yeah. Mm-hmm. Heck yeah. Well, thanks for hearing that. That's part 1. Beginning to get into chapter 3 right now. Bacteria. Gonna have a quick smoke. Yeah, the MORE Act has passed. Oh shit, it happened. Hold on, I'm reading this. Oh damn, yes. U.S. House of Representatives vote to end federal marijuana prohibition. In a historic vote more than 80 years in the making, the House of Representatives this afternoon approved the MORE Act, a bill that would end the federal prohibition of cannabis. The bill officially passed by a vote of 228 to 164 at 1:10 p.m. on Friday, December 4th. This is the first significant congressional action on marijuana since the passage of the Marijuana Tax Act of 1937, which federally criminalized all aspects of cannabis production, sale, and possession. The MORE Act will now move to the Senate, where it's widely expected to be blocked by Senate Majority Leader Mitch McConnell. Yeah. Oh God. We'll see how that goes. So through the House, now it's on to the Senate, friends, and we'll see how it goes. So I mean that's iconic. This is big. This is really big. I'll smoke to that shit. Yeah. So that's awesome news. Yeah. Shit, they fucking voted for him already. There's no use saying that, you know. Kentucky voted to keep him. What's wrong with those fucking people? Sorry, I'm trying to get this dab out of here without getting a big old glob. It's the bourbon. It's dissolved their brain cells. That tends to occur for alcoholics or something. Celebration. Yes. So, good job, government. You did something nice this year for once. Federal government, the House. Let's see what happens next. Alright. Alright, so I'm gonna read chapter 3 of Teaming with Microbes before we go on with the rest of our broadcast for the day. Thank you so much for hanging out while I do this. I actually wish to get back into my gardening and learning again, as I'm in a period of time where my physical activity in regards to cannabis cultivation have been reduced immensely. I need to just hit the books. I need to get back into it so that I could relearn some things, as well as take on more as I begin to take on more responsibility down the line for what I do here for our cultivation sites. And, you know, like I always talk about some of these things, and I wish to be able to explain further in depth some of these things that I talk about based on what I learned through my field training, working for an organic farm, participating in composting, and taking samples of the soil to look at the health of the soil, the microorganisms therein and stuff, and to be able to regurgitate this information to you guys as well. To the folks that are chilling and want to learn more about live soil and natural gardening, this is what you need to know to really understand what's happening, to get it to work naturally. There's so much that you can do to the soil itself without the use of the artificial supplements, you know. We were talking the other day about using salt-based supplements, like liquid-based supplements versus naturally working the soil food web and stuff. There's natural defenses and supplements that you can create through healthy soil that you can't really achieve without assisting your artificial grow. If you're doing it with inert soil, you're doing it with stuff that's just using your salt-based chemicals and stuff, you know. I'm using them, but I don't have the benefit of those microorganisms in the soil defending the plant from things like, you know, it's in a grow tent and we're nowhere near the outdoor gardens and stuff, but somebody could walk through a bag garden, someone could go through a rose garden with the PM and stuff, the powdery mildew, and straight up just make that plant more susceptible. It's more susceptible to those things, and will need assistance to recover, versus having the live soil that will build natural defenses and help fight off any invasive pests, the culture, the microorganisms. Through this last chapter, we understood that we learned more and are beginning to understand that bad soil can promote an anaerobic environment where you could have nasty microorganisms that are pretty much making it harder for the plant to survive, killing the plant, killing plant cells. I always talk to you guys about the balance, and it is totally that. Soil chemistry, water chemistry, or something that we talked about heavily the type of water that you use, what's in it, your soil, what you use, what's in it, your light source, the environment itself, air circulation, temperature, humidity, um, the yeah, that was it. Soil chemistry, water chemistry, your AC equipment, your environment, internal, external, your light source, your genetics. It all plays a major role in the cultivation process and like a successful garden growing to fullest potential, if you will. Hello, welcome to the sesh. Oh. Excuse me. I'll take another bomber before I get back into it. Yeah. I'm going to take the time to read. When I do yoga in the morning, I'll also go ahead and do some reading with everyone before we get back into our other session. Yeah. So do bear with me while we do our exercises and reading. I'm trying to improve all aspects of my life, be a better gardener, feel better about myself physically, mentally through exercise and yoga, and then continue my passion and work by sharing it with you guys. So, yeah. Yeah, humidity's big. Oh, absolutely. That was part of what I was saying about the balance. I briefly said it when I first said it, but light source, AC, which is airflow, temperature, humidity. Yeah, you really need it up there because that affects nutrient intake as well. Imagine you have an environment that has a hell of a lot of humidity, 100%. I was talking earlier about how plants intake nutrients through the root system, in between plant cells that make up the plant, like a series of hallways, borders, and checkpoints, and then in between, or sorry, directly through the plant cells. Directly through the plant cells, in between the plant cells, through the root base. And so you have an environment that's 100% humid. The humidity is just 100%. There's moisture in the air just all the time. So that plant is getting hit with all that water all the time. And that's going to make the plant want to just shut down. Intake when the plant intakes water and supplements through these outlets, it's like a series of borders and checkpoints. These borders and checkpoints, they want to make sure that nothing bad gets through, or the least amount of the bad people get through. And so the borders and checkpoints are hit, slammed, very hard, all the time. It's just like fucking everybody's trying to get in. It's overcrowded. These checkpoints, at this point, the safest thing to do would be to shut them down. And so your plant shutting off the capability of intaking any more moisture or nutrients from that level will go into a point nutrient lock, or they'll just sit there and not take in anything more, and then like maybe it's something where the soil's not got proper flow. Yeah. Oh, absolutely. Yeah. So what Tree Herder said is true as well. You'll have plants like if it's transpiring and you get rid of that shit, you're good. You know, there's environments where you have that higher humidity, and the plant's gonna just fucking do what it can to survive. And if it's able to actually like wick off that extra shit, you know, what is transpiring, and it's not just being hit all the time with that moisture and humidity. It could survive in veg, totally. Yeah. Thank you so much for gifting that sub there, man. Yeah. Oh, yeah. Yeah, veg is cool. Like, you don't want that shit during flower. You don't want too much of it during, sorry, heavy wet soil base that's not draining water. If it becomes waterlogged, that's something that can affect it. You know, and then what I was describing about hitting the plant with too much water, it'll just not want to intake water. So you're like sitting there and you're pouring through and you're giving it water. Some of it drains, some of it rests. It's sitting there. It changes the environment there for the soil. The microorganisms aren't gonna like that business. Um, we were just talking about that about how top feed water is going through the soil base, and what was it when this gravitational watering occurs, there's new air being pushed through the soil, and where there are these pockets in the soil, the pores that are keeping the oxygen, it's trying to push out that old stale air and oxygen, and get the airflow through there. And then like when it's not properly draining and it just fucking stuck, and it's just stuck like that, it's gonna be shitty for your environment. Yeah. Yeah, we just read about it and everything. I shared on Twitter myself. Yeah. Mm-hmm. Oh yeah. All right. I get one more bowl, and then I'm gonna read chapter 3, bacteria. Um, Teeming with microbes. The Organic Gardener's Guide to the Soil Food Web, revised edition. Jeff Lowenfels and Wayne Lewis. Chapter 3, bacteria. Um, yeah, no worries, no worries. What? No, it's totally fine for it to. The plant's intaking water through all those means. We were talking about excess moisture being bad. Um, in certain environments. Like I knew a person that was growing, and they were across the street from a water treatment facility where the fucking nasty hard water from the plant from the water treatment plant was in the air and affecting his plants. It was like fucking um, it was building up in the windows in the house. It was in the grow. It was all over the plants. This hard water with stuff in the water. High humidity with a different content. Because you could talk about 100% humidity, moisture in the air, but what's in the water? You know, chlorine content. Excess chlorine promotes the byproduct chloramines. The water could be a certain pH, too acidic, and then that's just hitting your plants too hefty. You know, that's different from you watering your plant, transpiration occurring and getting into the air. That's like an internal environment thing. If you're growing inside and that's occurring, and transpiration and higher humidity from that, the plant's recirculating the moisture, throwing it back into the air, that's different from something like the moisture in the air from those environments like I described, or something else in your water that you're not paying attention to. So many factors go into it, dude. So many factors. Forest itself is a container for moist air. Absolutely. Yep, it traps it there. Mm-hmm. We were talking about. I was talking to Eve about places like around me, Maine, East Coast forest that I went to, uh, like Mount Appetite versus uh, where I live, Forest Falls. That forest, the tree line, the conditions of everything based on the weather, moisture content in the air, the desert arid climate. Um, you could see it like where I live, Forest Falls in that area. The tree line is very sparse. There's more light going through the canopy in the entire forest. East Coast Maine, there's higher humidity. The weather is different there. The weather is being trapped, like the moisture in the air is being trapped in there, in the forest as it's thicker canopy. It's the soil's alive compared to the desert climate, all arid, compact clay. Out there, you've got a different type of soil going down. We learned that today. I didn't know that about lichen and shit. That lichen is actually eating rocks and breaking them down into smaller bits, and that is what helps contribute to the creation of this like environment, the soil and stuff, the different type of soil. It just really depends. Oh man, super cool. So much to learn. Oh god, deciduous forest are where you live? Did I say it right? Deciduous? Deciduous? Deciduous. Oh boy. Mm-hmm. Oh, very cool. Alright. I'm going to get into Chapter 3, Bacteria, teeming with microbes. Teeming with Microbes, The Organic Gardener's Guide to the Soil Food Web. Revised edition. Jeff Lowenfels and Wayne Lewis. Chapter 3, Bacteria. Bacteria are everywhere. Few gardeners appreciate that they are crucial to the lives of plants, and fewer still have ever taken them into consideration. Yet, no other organism has more members in the soil, not even close. In part, this is because these single-celled organisms are so minuscule that anywhere from 250,000 to 500,000 of them can fit inside the period at the end of this sentence. Bacteria were the earliest form of life on Earth, appearing at least 3 billion years ago. These prokaryotes, they are prokaryotes. Their DNA is contained in a single chromosome that is not enclosed in a nucleus. Their size, or more precisely, their lack thereof, must be the main reason our familiarity with bacteria is usually limited to the diseases they cause and the need to wash our hands before eating. Most baby boomers use a standard issue 1000-power microscope to study microorganisms, but bacteria are too small to see in any detail at this power. School microscopes have gotten better, and some lucky students now do get a closer look, literally, at bacteria. The three basic shapes, all represented in the soil, are coccus, spherical or oval, bacillus, rod-shaped, and spiral. Yeah. Don't have nucleus. Did I say something? Yeah. They are prokaryotes. Their DNA is contained in a single chromosome that is not enclosed in a nucleus. They don't have a nucleus. So, bacteria reproduce, for the most part, by single-cell division. That is, one cell divides and makes two cells. They each divide again, and so forth. Amazingly, under laboratory conditions, one solitary bacterium can produce in the vicinity of 5 billion offspring in a mere 12 hours if they have enough food. If all bacteria reproduced at this rate all the time, it would take only months or so to double the mass of our planet. Fortunately, soil bacteria are limited by natural conditions. Predators, protozoa chief among them, and a slower reproductive rate than their laboratory cousins. For example, bacteria must have some form of moisture for the uptake of nutrients and the release of waste. In most cases, moisture is also required for bacteria to move about and to transport the enzymes they use to break down organic matter. When soils become too dry, many soil bacteria go dormant. Bacteria, incidentally, rarely die of old age, but are usually eaten by something else or killed by environmental changes, and then consumed by other decomposers, often other bacteria. Yeah. Same. Oh gosh. Photocomposite of the three basic shapes of bacteria: coccus, bacillus, and spiral. 800 times magnification. Primary decomposers. Despite their tiny size, bacteria are among the Earth's primary decomposers of organic matter, second only to fungi. Without them, we would be smothered in our own waste in a matter of months. Bacteria decompose plant and animal matter in order to ingest nitrogen, carbon compounds, and other nutrients. These nutrients are then immobilized inside the bacteria. They are released, mineralized, only when the bacteria are consumed or otherwise die and are themselves decayed. Yeah. Different kinds of soil bacteria survive on different food sources, depending on what is available and where they are located. Most, however, do best decomposing young, still fresh plant material, which composters call green material. Green material contains lots of sugars, which are easier for bacteria to digest than the more complex carbon compounds of other plant material. Composters call this brown material, and until it is broken down into smaller carbon chains, other members of the soil food web more readily digest this than do bacteria. Yeah. Wow. Yeah, that's awesome. Right? We were talking about for the longest time, they're constantly talking about bacteria that they're finding in Greenland in the permafrost. As the permafrost is like kind of going away, they're seeing all sorts of things out there, and the bacteria like that has just been dormant. It isn't dying. That's really cool. Given their diminutive size, bacteria must ingest what are necessarily even more tiny pieces of organic matter. How do they do this? The short answer: they take in food directly through their cell walls, which are composed, in part, of proteins that assist in this molecular transport. On the inside of a bacterium's cell wall is a mixture of sugars, proteins, carbons, and ions, a rich soup that is out of equilibrium with the less concentrated mixture outside the cell wall. Nature likes to try to keep things balanced. Normally, water would flow from the dilute solution without into the wait. Nature likes to try to keep things balanced. Normally, water would flow from the dilute solution without into the more concentrated one within a spectral form of diffusion as osmosis. Water would flow from the dilute solution into the more concentrated one with special form of diffusion known as osmosis. I think there was a typo. But in the case of bacteria, cell walls act as osmotic barriers. Ooh. Molecular transport across the cellular membrane is accomplished in several ways. In the most important, active transport, the membrane proteins act as molecular pumps and use energy to suck or push their targets through the cell wall. Nutrients in, waste products out. Different proteins in the membrane transport different kinds of nutrient molecules. One way to imagine this is to think of an old-fashioned fire bucket brigade, in which the water was passed from its source to the fire. These proteins pass buckets of nutrients into the cell. Active transport is a fascinating but complicated process fueled by electrons located on both sides of the membrane surface. The gardener should certainly be aware of and appreciate how bacteria feed, but only needs to understand that bacteria break up organic matter into small, electrically charged pieces, and then transport these through their cellular membranes, ready for use. Once inside the bacteria, the nutrients are locked up. Other members of the soil food web obtain their energy and nutrients by eating bacteria. If there aren't sufficient members of bacteria in the soil, populations of these members of the soil food web suffer. Bacteria are part of the base of the soil food web food pyramid. They don't die of old age. Yep. That's crazy. Some bacteria very deep in the earth may live for thousands of years, millions. Yeah, we were just talking about in the other chapter the different layers of the soil that we work with, and the gardeners only work with a couple layers at the surface, and there's layers that are very difficult for us to like even fucking see the difference between them, and breach, and there's still some things there alive. Yeah, we mostly see it all at the surface. It's comparable to what we talk about trees, where there's huge trunks to the tree, But what's really alive is mostly what's on the outer surface, kind of thing. Yeah. The rest of it's all like being broken up, weathered away as it starts to reach the surface. Like we were talking about the lichen that are consuming the rocks. The rocks doing their thing. You got the Earth's tectonic plates jutting and protruding and smashing against each other and bringing shit up to the upper parts of the surface of the Earth's crust and the towards the soil base. Yeah. There you go, right on. 50 watt grow lamp to 600 watt grow lamp. Problem, it made the grow box pretty hot. Top of the box freeze 90F. I have left the door. I crack open, letting cool air in from the bottom. Hot air out from the top of the door. Yeah, just get a little airflow in there. 2.8 kilometers below the surface. They could exist, huh? Crazy, right? Sorry. In that crazy gold mine in Africa? Holy shit. Well, see, you got all that other stuff going on in there too, right? Oxygen, airflow, the different microorganisms feeding off of the rock, doing their thing. They don't need oxygen, or they don't need daylight. They don't need that. They're just trying to thrive. Yeah. That's one of those environments where you would see a hell of a lot more of the bacteria versus fungi. Right? Oh, tardigrades. Yep. Yeah, oh, I love those things. Yeah, the tardigrades. Yeah. Oh, that's alright. Yeah, it's crazy to see those different kinds of things. Or like we were talking about the caves in New Mexico that are growing the giant quartz crystals and shit. The silica crystals. And the water down below, like it's flooded and it's hot as fuck. We can't survive down there on our own. There are fish down there, living in the hot water. You know, obviously there's other forms of freaking life down there as well. You know, and it's something that they're totally a-okay with, adapted to that hotter environment, right? Very interesting stuff. Okay, sorry. Let me continue. Teeming with microbes. Chapter 3. Bacteria. Feeding bacteria. Root exudates are favorite foods for certain soil bacteria, and as a result, huge populations of them concentrate in the rhizosphere, where bacteria also find nutrition from the cells sloughed off during root tip growth. But not all soil bacteria live in the rhizosphere. For fortunately, organic matter is almost as ubiquitous as bacteria. All organic matter is made up of large, complex molecules, many of which consist of chains of smaller molecules in repetitive patterns that usually contain carbon. Bacteria are able to break the bonds along certain points of these chains, creating smaller chains of simpler sugars and fatty and amino acids. These three groups provide the basic building blocks bacteria need to sustain themselves. Bacteria uses enzymes both to break the bonds holding organic chains together and to digest their food. All this is done outside the organism before ingestion. Untold numbers of enzymes are employed by bacteria, who have adapted over the millennia to attack all manner of organic and even inorganic matter. It is an astonishing feat that bacteria can employ enzymes to break down organic matter, while at the same time not impacting their own cell membrane. Is there any pictures there? Sorry, I'm trying to show you guys the pictures too. Oh, we're already looking at that one. Alright. Air and no air. There are two main groups of bacteria. The first, anaerobic bacteria, are able to live in the absence of oxygen. Indeed, most cannot live in its presence. The bacterial genus Clostridium, for example, does not need oxygen to survive and can invade and destroy the inside soft tissue of decaying matter. Byproducts of anaerobic decay include hydrogen sulfide, think rotten eggs, butyric acid, think vomit, ammonia, and vinegar. This raises questions about certain smells in cannabis and flavor. The notorious E. coli and other bacteria normally found in the mammalian gastrointestinal tract, and thus in poorly made manure-based compost, are facultative anaerobes, meaning they can live in anaerobic conditions if they must, but prefer anaerobic environments. Most gardeners have smelled byproducts of anaerobic decomposition, perhaps in the garden, but certainly in the refrigerator. These are smells to remember when composting and gardening with the soil food web, because anaerobic conditions foster pathogenic bacteria and, worse, kill off beneficial aerobic bacteria. The other major group of bacteria, those that require air. Most facultative. Most facultative aerobic bacteria are able to live in anaerobic conditions if they must. Most cannot. Aerobic bacteria are not normally known to cause bad smells. In fact, the actinomyces. Oh gosh. Science! The actinomycetes, or order Actinomycetales, specifically the bacterial genus Streptomyces, produce enzymes that include volatile chemicals that give soil its clean, fresh, earthy aroma. Anyone who has gardened recognizes this smell, the smell of good soil. Science! How the fuck do you pronounce this? Right? One more time. Actinomycetes. Sorry. Actinomycetes are different from other soil bacteria. They actually grow filaments, almost like fungal hyphae. Some scientists believe Streptomyces species use their branching filaments to connect soil particles, so they, along with the soil particles, become too big to be eaten by their natural predators, the protozoan ciliates, which would engulf and ingest them. Actinomycetes are particularly adept at decaying cellulose and chitin, too difficult to digest brown carbon compounds. The former found in plant wall cells, and the latter in fungal cell walls and in arthropod shells. These are not normal foods of other bacteria. Actinomycetes are also adapted to live in a wider range of pH than other bacteria, from acidic to alkaline. Bear with me, friends. Decay of cellulose. Cellulose, a complex carbohydrate made up of long chains of carbon-based glucose, is the molecular material that gives plants structure. Yeah. Lactobacillus. Oh, I know that. I knew that one. Mm-hmm. It constitutes half the mass of plant bodies, and hence half the mass of organic matter created by plants. Specialized bacteria, likely the aptly named Cellulomonas, carry cellulose-breaking enzymes that they release only when they come into contact with cellulose. As opposed to the random release of enzymes by other bacteria who eat in a hit-and-miss manner. Most bacteria reach their limit when it comes to the non-carbohydrate lignin. Another prevalent molecularly complex plant material. One more time. Most bacteria reach their limit when it comes to the non-carbohydrate lignin. Another prevalent molecularly complex plant material. Lignin, the tough brown component of barks and woody material, is a much more complex organic molecule than cellulose, made up of chains of interlinked alcohols. These are resistant to the enzymes produced by most bacteria and are left for fungi to decay. Element cycling. One way of looking at decay is to view it as nature's recycling system. Bacteria in the soil food web play a crucial role in recycling three of the basic elements needed for life: carbon, sulfur, and nitrogen. For example, CO2, carbon dioxide, is a major byproduct of aerobic bacterial metabolism. Carbon tied up in plant and animal biomass is cycled in CO2 gas during decay. Photosynthesis in higher plants converts the CO2 into organic compounds, which are eventually consumed and then recycled back into CO2. Similarly, sulfur is recycled. Sulfur oxidizing bacteria use the element to make plant-available water-soluble sulfates. Liberated from organic materials by anaerobic bacteria, sulfur-containing compounds are produced by chemoautotrophs. Chemoautotrophs, bacteria that get energy from oxidation of sulfur. The nitrogen cycle, propelled in part by specialized bacteria, is one of the most important systems in the maintenance of terrestrial life. Living organisms produce the vital organic compounds, the building blocks of life, amino and nucleic acids, using nitrogen. The strong bonds holding atmospheric nitrogen molecules together make this nitrogen inert for all practicable purposes and useful for plant needs. For plants to be able to use nitrogen, it has to be fixed, combined with either oxygen or hydrogen, producing ammonium, nitrate, or nitrate ions. This important process is called nitrogen fixation. Certain bacteria convert nitrogen from the atmosphere into plant-available forms. The genera that accomplish this nitrogen-fixing feat are Azotobacter, Azospirillum, Clostridium, and Rhizobium, any of which could be a great name for a comic book superhero. Azotobacter, Azospirillum, and Clostridium live free in the soil. Rhizobium species actually live in the root tissues of certain plants, particularly legumes, where they form visible nodules. We don't mean to suggest you need to memorize the species of soil bacteria, but we do want you to focus on the fact that nitrogen fixation as well as the recycling of carbon and sulfur, requires the interventions of living organisms. These are always taught as chemical processes, but they are really biological. Yeah. Um, the nitrogen cycle, courtesy Tom Hoffman, graphic design. Oh, look at that. That's really nifty. Yeah. Oh. Oh. Yeah. Bacteria carry out these processes in the soil, forming symbiotic relationships with specific plants or existing symbiotically within organisms. Sounds like a case of the biology creating the chemistry of us. Um, yeah. Mm-hmm. Through a couple different means. They're taking in a bunch of other nutrients, holding onto them like a fertilizer bag. They're sitting there linking with the plants and passing along some nutrients like a fire brigade with buckets, described in the book. Mm-hmm. Then you need the other shit to eat them so that you can spread the rest of the nutrients in the soil after it's become locked up and inert. Yeah. Oh, another part of the nitrogen cycle, the place at which it starts in the soil, involves the decomposition of proteins into ammonium. This ammonium usually figures as part of the waste product produced by protozoa and nematodes after eating bacteria and fungi. Next, special nitrate bacteria, Nitrosomonas, convert the ammonium compounds into nitrates. A second type of bacteria, nitrate bacteria, convert the nitrates uh, into nitrates. Yeah. Convert the nitrates into nitrates. Nitrifying bacteria do not generally like acidic environments. Their numbers, and hence the conversion of nitrogen into nitrates, therefore diminish when soil pH drops below 7. Bacterial slime, already mentioned for its ability to bind soil particles together, happens to have a pH above 7. Thus, if there are enough bacteria in an area, the slime they produce keeps the pH in their vicinity above 7, and nitrification can occur. If not, the ammonium first produced by organisms in the soil is not all converted to nitrate form. If the pH is 5 or lower, very little, if any, of the ammonium is converted. Denitrifying bacteria convert nitrogen salts back to N2, which escapes into the atmosphere. Obviously, denitrifying bacteria do not help the fertility of soil, but they are essential in that they keep the nitrogen cycle moving. Biofilms. Bacterial slime, or biofilm, is a matrix of sugars, proteins, and DNA. The fact that bacterial slime in the soil is slightly alkaline not only influences the pH where it counts most, in the rhizosphere, but also buffers the soil in the area so the pH remains relatively constant. Some bacteria use their film as a means of transportation, literally squirting this substance as a means of propulsion. Most bacteria, however, travel using an astonishing bit of natural nanotechnology with the aid of one of our more whip structures, or flagella, that resemble and operate like propellers. Biofilms save bacteria from desiccation as the soil dries. Soil bacteria often live inside sticky globs of biofilm, complete with an infrastructure of channels filled with water for transport of nutrients and waste. Biofilms can also be a defense against antibiotics produced by other organisms, including fellow bacteria. Bacteria colonies protected by slime are 1,000 times more resistant than individual bacteria to antibiotics and microbicides, sorry. Oh. Scanning electron microscope of a biofilm surface. Insect parts and plant fibers are embedded in the slime, along with numerous crystals. And then bacteria biofilm on stainless steel, 1,600 times magnification.
That's what she said before she left. Fuck you, Solo, damn it. Yeah.
Oh, so sorry. Oh, I hope you're good. Yeah. Sorry. Oh, yeah. So we were looking at the biofilm that makes up the bacteria, learning a little bit about the different bacteria doing their thing. Yeah. All right. Moving on to the last few pages before we complete this section. Nutrient retention. Bacteria play a major role in plant nutrition. They lock up nutrients that might otherwise disappear as a result of leaching. They do so by ingesting them while decomposing organic matter and retaining them in their cellular structures. Since the bacteria are themselves attached to soil particles, the nutrients remain in the soil instead of being washed away, as is the case with chemical fertilizers. Indeed, these nutrients will be tied up, immobilized inside the bacteria until the bacteria are eaten and reduced to waste. Since soil bacteria don't travel very far, and there is ample source of bacterial food in the root zone, the nutrients ingested by the bacteria are kept in the vicinity of the roots. Other organisms, such as protozoa, play major roles consuming bacteria, releasing excess nitrogen as ammonium in their wastes, which are deposited in the rhizosphere, where the roots can absorb nutrients. Oh, sorry, right where the roots can absorb nutrients. Yeah. Other benefits of soil bacteria. Some anaerobic bacteria produces alcohols that are toxic to plant life and to other bacteria. These anaerobic bacteria can be avoided when gardening by controlling the conditions that allow them to multiply. Poor soil texture, lack of pore space, standing water, and compacted soil. Other bacteria are pathogens that cause disease in higher plants. The list of pathogenic bacteria is a long one, including bacteria that causes citrus canker, diseases of potatoes, melons, and cucumbers, and fire blight of pears, apples, and the like. Thousands of bacterial pathogens are in soil, and billions of dollars are spent every year to protect crops from damage by the culprit bacteria. Agrobacteria, oh god. Tumefaciens cause galls or tumors to grow on the stems of certain plants. Burkholderia cepacia is a bacterium that infects and rots the roots of onions. Some Pseudomonas species cause leaf curl and black spots on tomatoes. Despite the presence of pathogenic bacteria, there are more benefits to a healthy soil bacteria population than not. For example, bacterial activity is also often responsible for breaking down pollutants and toxins. These processes are usually aerobic, requiring oxygen to occur. You undoubtedly have heard of the bacteria that can eat oil spilled on a beach in Alaska. There are similar bacteria that will eat gasoline spilled on your lawn, for example. Soil bacteria produce many of the medicinal antibiotics upon which we have come to depend. One could only speculate that since these bacteria have to compete not only with other bacteria for nutrients, but also with fungi and other organisms, they evolve protective capabilities. For example, Pseudomonas bacteria can correct take all, a disastrous fungal wheat disease, by producing phenazines, very strong, broad spectrum antibiotics. Obviously, many soil bacteria keep pathogenic bacteria in check, a big benefit of healthy soil food web. All bacteria um, compete with each other and with the other organisms for a finite amount of food the soil offers, and thus keep each other's population in balance. Soils with a high diversity of bacterial types are more likely to have larger number of non-pathogenic bacteria outcompeting pathogenic bacteria for space and nutrients. We are convinced that using the soil food web's natural defenses is the best way to keep the bad guys in check. Gardeners need to appreciate that bacteria are at the front line of defense. Yeah. Oh, you don't need to take notes. I'll make sure to highlight these so that you could like listen in to me trying to read science to you on YouTube if you want. You gotta pay for the book, but it ain't cost you nothing to listen to PodQuest read it to you. Ugh. Holy Moses. Thank you guys for sticking through it, hearing me out for chapters 1 through 3 so far of Teaming with Microbes. We were basically trying to cover the basics, the soil food web as a whole, understanding our soil, being able to understand the basic components of our soil, the soil food web. Soil food web being bacteria, fungi, ciliates, flagellates, microarthropods, the protozoa, nematodes, the balance, beneficial, non-beneficial. You can have non-beneficial bacteria present in your garden, in your soil, but it doesn't necessarily mean it's a bad thing. Too much of a good thing could be a bad thing as well. We were talking about the anaerobic environment a lot today. We've been trying to understand more about it. Anaerobic bacteria, microorganisms that can produce alcohols that destroy plant cells. They thrive in environments in soil where there is lack of oxygen. And then we learned about like knowing these different things, you could understand like what you can do to mend your soil and get it back in working order. We talked about how having all of these different things in the soil food web and beyond, in the garden, helps do different things. Their relations, the predator and prey, the cohesion between partners. Of all these like bacteria, how the plant bonds with fungi, mycorrhizae association, the manner in which these things can produce chemicals and convert chemicals from one thing to another. Reading this and learning more, I'm actually like I'm understanding what's happening to soil in certain examples in the past, where it's like, well, now I know why I fucking smell ammonium in the soil. There's lack of a certain bacteria that's converting the ammonium into nitrate. So, I mean, that's something that's like on my level of somebody that's like trying to to understand it all. I've got a basic understanding of the soil food web already, and what's in it. Now that we're reading the book together aloud and learning about certain bacteria, certain microorganisms in the soil, and aerobic bacteria, anaerobic bacteria, learning about what I've seen, what I've already known, but a new perspective. It's super awesome.